Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Image of Center of the Milky Way Galaxy Reveals How the Universe Works. The Milky Way Galaxy is 100,000 light years in diameter. And this is illustrated here. This would be what our galaxy is expected to look like from outside if viewed edge on. And it has this bulge, it's called the central bulge, which is much brighter. Now, a light year is the distance that light travels in 1 year and corresponds to 6 trillion miles or 10 trillion kilometers. So it's a huge distance. So we are looking at a huge object in space, a galaxy. And our sun is expected to be about here, about 28,000 light years from the center of the galaxy. Now, what we also see is these lights, these circular points of light, and these are actually globular clusters, and these are spherical collections of stars which orbit the galactic nucleus, so are gravitationally bound to the galaxy. And this is what a globular cluster looks like. It's a compact spherical collection of stars which are tightly bound by gravity. Now, star clusters may have from 50 to 100,000 stars in them. So the fact that they are tightly bound suggests that they are young stars. As stars lose, or they are made up of young stars. As stars lose gravitational influence as they age. So the whole globular structure, globular cluster, would tend to move apart as it ages. Now, the galactic bulge seems to extend for some 20,000 light years, but the nucleus of the galaxy is much smaller. The galactic nucleus of the brightest galaxies only extends for about 100 AU, which is the size of the solar system. The fact that these galaxies are so bright would indicate that they produce extremely strong electric fields and are therefore high energy bodies, and since energy is associated to gravity, they would therefore have stronger gravity. The stronger gravity would allow the nucleus to pull in matter more strongly and would cause the galactic nucleus to be smaller than galactic nuclei that are not as high in energy and consequently not as bright. Since our galaxy is not one of these very bright galaxies, the galactic nucleus may be larger, perhaps 1,000 AU in size. But this is still much smaller than 1 light year, since 1 light year is 63,000 AU. Therefore, the galactic nucleus is a tiny portion of the bulge. The brightness of the bulge comes from stars and clusters of stars that are very close together and much closer than they are further out from the nucleus. Although it is widely believed that there is a supermassive black hole at the center of most galaxies, the stellar cores which have invaded our solar system have shown that this is impossible. Stars have dense solid cores like planets do and do not collapse gravitationally. In fact, quite the opposite happens. They lose gravity and expand as they get older, because an object's gravity or gravitational influence depends on the photon energy in the particles making it up. And this energy decreases as an object ages. We would therefore expect the youngest objects to be smaller and brighter than older objects. Thus, active galactic nuclei are most likely nuclei of young galaxies. And here we see an active galactic nucleus. This is an active galaxy that must have an active galactic nucleus at its center. And these are very energetic galaxies, though they eject a lot of materials. You can see large amounts of plasma here coming from the center. And these emit radio waves. And these are also the active galaxies are extremely bright, and the nucleus of these galaxies is extremely bright. And so this shows that they are very strong energetically, and therefore would produce a very strong gravitational field, and that would mean they would be very compact and also young, very young. Now, Alton Harp, the astronomer that wrote the book Seeing Red, discovered that these active galaxies eject material along their minor axes, which are perpendicular to the plane of the galaxy, which condense into quasars, which in turn form galaxies. So these active galaxies give birth to other galaxies. And in time, these galaxies age and become older galaxies, like our galaxy seems to be, because it's not so as bright at the center. And so if galaxies eject material that turns into new galaxies, then it is to be expected that they also eject smaller amounts of material, which turns into star clusters, and also even smaller amounts of material, which turn into star systems with stars and planets in them. It is also likely that the older galaxies, which are not as bright or as energetic, eject smaller amounts of material, which condenses into star clusters, whilst younger galaxies eject large amounts of material, which turns into new galaxies. Since our galaxy does not seem to have an extremely bright center, it is most likely an older galaxy and would be expected to eject smaller amounts of material at a time. The large number of star clusters observed close to our galaxy and orbiting around it seem to indicate that these are most likely the product of ejections from the center of our galaxy. Recently, a radio telescope image of the center of our galaxy, or the Milky Way galaxy, has been obtained. And the image covers a large region. It extends 1,000 light years horizontally and 500 light years vertically. And since the actual nucleus will occupy a very tiny part of the entire region seen, it is likely that what we do not see, that we do not actually see the nucleus, but the material that the nucleus has recently ejected and which is still close to it. So the nucleus would be a very tiny region, a tiny, tiny speck in this whole region seen here. And we see many circular structures, which are most likely globular star clusters in a formation stage. And we see long filaments, and these are puzzling at first. But these would have to be long ejections of plasma from condensed material not far from the galactic nucleus. And this suggests that they may be more than one very large and dense galactic nuclei type structure within the center of the Milky Way galaxy. So these are probably originate from large objects that have dense cores that are able to eject material like the galactic nucleus can. And there is still one region which is brighter than all the regions, so this is most likely where the original or the largest galactic nuclei type structure is, and one that is ejecting a large amount of materials. You can see from this very large and bright ejection here, it's ejecting material along here, and this is likely to be material that it has ejected as well. So the galactic nucleus must be somewhere there, inside there. Now, in order to start ejecting light, which turns into matter, an object needs to undergo condensation so that a core is formed. Plasma ejections coming from a galactic nucleus would be expected to be far out of this region before they are able to do their own ejections. But we are seeing ejections coming from different points in this region. This could be because as a galactic nucleus ages, it expands and then breaks into separate different pieces. And here we see a close-up of that central region. And this long curving ejection is most likely coming from this most energetic region. And this would be where we would expect to find the nucleus of the galaxy. The nucleus is thus most likely situated right here, where this long curving ejection seems to be coming from. Now, as pointed out before, the fact that galaxies have so many globular structures surrounding them suggests that these form close to the center of galaxies and are ejected outwards, which would explain why we see so many large circular light-emitting agglomerations of plasma. Many of these large structures, which would be several light years in length, are still inside more diffuse clouds of plasma. These are most likely younger and thus closer to the nucleus. And let's look at those. So these are the ones I'm referring to. These denser agglomerations that are most likely globular structures and will turn into globular clusters. But they are still within plasma that must have come from the center of the galaxy, from the galactic nuclei there. So these would therefore turn into clusters of stars eventually. And so these will also be younger and thus closer to the nucleus, but will in time move further away from it and at the same time condense into a cluster of stars. It's also likely that most of the ejection is along what becomes the major axis of the galaxies, or along the plane of the galaxy, and that therefore the whole galaxy is made of star clusters that separate in time and populate the arms of the galaxy. Globular clusters would also tend to start out compact, as I mentioned before, but with time energy and thus gravity would decrease, and therefore the stars would move apart and the cluster would be much less compact. Now, all objects in the universe seem to operate in a very similar manner, so that both stars and planets have solid dense cores and generate energy through fission or through the decay of unstable nuclei. You may look at article 240 entitled Planet X System, Effect on Radioactive Decay Rate and Heating of Planets for more details on that. The gravitational interaction becomes the strong interaction within the nucleus of an atom, and thus when the energy within particles drops and gravity drops, so does the strength of the strong force, which in turn causes the splitting of atoms or fission to occur more easily and thus more often. In other words, the radioactive decay increases. Decay rate, increases. This is illustrated here how a heavy nucleus splits into two smaller nuclei and at the same time releases energy in the form of high energy photons. Since all matter seems to operate in the same way everywhere, so that planets and stars operate in a similar manner to atoms, it is likely that a galactic nucleus would operate in the same way as well. However, a galactic nucleus would be expected to have a much denser core than a normal star, and thus will most likely have extremely heavy nuclei in its core. In other words, there would probably be nuclei in it that we have never encountered, and with atomic numbers much higher than that of uranium, which has an atomic number of 92, and even higher than the highest atomic number on the periodic table, which is 118. The atomic number of an atom corresponds to the number of protons in that nucleus. So fusion is expected to occur after light is emitted by the galactic nucleus, which then turns into matter. When the matter emerges from within extremely high energy photons and the electric field in the environment is extremely high, an extremely strong gravitational interaction results, which leads to an extremely strong attractive force between protons, which will thus fuse into extremely heavy nuclei. As energy is expanded and time goes by, lighter elements down to hydrogen will form, but the heaviest elements will condense first and thus be very abundant in the first solid matter formed. These become the cores of celestial objects. And what we see here is what atoms look like. These are light nucleus, and it would have less electrons than a very heavy nucleus, and so a very heavy nucleus would have a region in the form of a shell at the outer edge of the atom where the electrons would be found. So they occupy this shell type region at the outer edge of the atom. Now, as matter gathers around the largest and denser cores, these turn into living stars. Smaller cores turn into planets, which operate in the same way but do not generate enough energy to emit light from their atmospheres. And you may look at Article 185 entitled Stellar Formation, Stars are Formed from Light, and Article 186 entitled Matter Condensation. As it is with the atom, so it is with a star. And this illustrates what a superatom, that is a celestial object, is supposed to be like. It has a very dense core where the heaviest nuclei are abundant and where most radioactive decay is occurring, thus generating the energy which powers the star or the planet. It thus produces an electric potential difference, which generates a high electric field in the outer layers and thus in the atmosphere. The outer layers would be, the layers would be less and less dense as we move outwards, and the least dense layer would be the atmosphere, which is gaseous. And then there would be a very high electric field in the outer region, and thus this would result in the largest objects, which would be stars, being able to emit extreme amounts of light from their atmospheres. So in conclusion, a radio telescope image of the center of the Milky Way galaxy indicates that the nucleus of the galaxy is ejecting material which forms clouds of plasma around the nucleus. Circular formations are likely to be globular clusters in a formation stage, which will eventually end up orbiting outside the galaxy or join the previously ejected stars that have populated the plane of the galaxy. Ejections are occurring from several different points, suggesting that the original galactic nucleus has expanded and broken into pieces. This agrees with the idea that gravity is associated to energy, and that as an object ages, it loses energy and therefore gravity, and thus expands, which may lead to the largest of these objects, such as galactic nuclei, breaking into pieces. And there are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.